All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hopefully, you guys are all doing okay. Someone coming in here, let me let him in. Okay, so let's actually jump into it. Let's go. Let's go. We're R04, and I think we're here. All right. So I had some examples for you guys to do last time. Hopefully you guys tried that. We're going to go through those. So I don't know if we need a recap, but last time we were talking about something called continuity, right? Very intuitive notion. The notion that you can, something has no disruptions, no breaks, no holes, no gaps, can, in theory, draw it without lifting your pencil off the page. It turns out that for that to occur, mathematically, all we have to verify is this equation that I have in a box right here. The limit as x approaches a of f of x is equal to f of a. And if that equation holds, then this property that I just described very intuitively will be true when you're close to a, right? For some small region or neighborhood around a. So that's good. If that equation holds for all values in the domain of a function, we call the function a continuous function. Okay. So we saw some examples of when this definition is satisfied versus when it's not, and we see that in all the examples that I showed you, when it's not satisfied, it's not continuous, and when it is, right? But of course, there's an infinite variety of examples. This is not a proof or anything, it was just sort of to give you a compelling reason to believe what I'm saying. As far as showing something is continuous, I want you to remember that there will be 3 things that I would expect you to be able to show. Like, so if I give you a random function and I ask you, where is this function continuous? Or show me this function is continuous, or something like that. I expect you to go through these 3 steps in some way, shape, or form. And the 3 things that must happen in order for that equation to be fulfilled is that the function must be defined at the point of interest, the limit must exist at the point of interest, and the value of the limit and the value of the function need to agree. They need to be the same. If any one of those things don't happen, then the function it's not continuous at the point that you're looking at. And so to show that something is continuous at a point rigorously, how I would expect you to do it is for you to go through these 3 steps. To show that something is not continuous, all you have to do is pick one of these that you know is not going to work out and show me that it's not going to work out. Any one of these failing is bad. Now, we also spoke about something called the elementary continuous function. So this is like our periodic table of functions for math people, right? So everyone who's not a math major, as far as they're concerned, all functions are of this type or combinations of this type. And these are the elementary functions that we work with. These are the nice functions. And in some sense, these are so well known and so important and so elementary that I'm not even going to require that you prove that they're continuous whenever they show up. So chances are, if I ask you to show something is continuous, it's going to be some weird combination of these, or maybe a piecewise function involving them or something like that. And that's what you have to do. But if I just give you a polynomial and ask you, it's continuous, like you don't have to show anything, right? So polynomials, rational functions, radical functions, exponential functions, log functions, and trig functions are continuous functions. As I mentioned here, this, not in our syllabus. Mentioned that a long time ago, I guess. There's no harm in reminding you of that. So trig, we're not concerned with trig, not in applied calc. Okay, so you can ignore everything that has to do with trig functions. But yeah, these are the elementary continuous functions. These guys are the guys that are continuous on their domain, as long as there isn't something that make them impossible to compute. Once we're able to compute a real number output for these, it is continuous at that output, at that input. And then I left you with some examples on trying to figure out where these guys are continuous. Spoiler alert, we actually know the answer for the first two, but I figured we'll go through some things where you know what the answer is. So when we're going through this process, you can convince yourself that, yeah, I kind of get that this will work all the time. And then we get into some that are closer to what I might ask you. Including the fact that sometimes I might make one of these numbers unknown, like the 6 will be like a K or something, and I'll ask you, what should the value of K be in order to make it continue? But all of that is, once you understand the concept, you'll be able to work on those. And I'm pretty sure there are a lot of problems like that in your homework. So that is just a quick recap of where we were yesterday. So now we're actually going to do those examples. And ask you guys to try them. And we're going to try them. So so far, what are the guesses here? Where is this continuous? The first one.
All real numbers.
All real numbers, right? So when I say where, I usually mean on what interval. So you would state that as -infinity to infinity. And of course, it's a polynomial. So if I go through these 3 steps, that's what I better find out the answer is. Where is the second one continuous?
I'm taking a total guess, but is it -infinity to 2 and then 2 to infinity?
Right. Is the 2 included? Like a square bracket?
No.
No.
Because it's
right.
a whole, right?
Yeah, because if you plug in 2, you divide by 0, right? So it can be anything less than 2, or we can be anything greater than 2. We cannot be 2 itself. What about this one? What did you guys think?
-infinity to 0, and then with a bracket, and then just a parentheses with 2 to infinity.
Like this?
Yes.
Okay. And this one? And how did you come up with that, by the way? Like, what was your thought process here? Like, what did you actually think?
If you like, when I graphed it as a piecewise function, and I canceled out the when you factor and everything, you wouldn't include the x, so you would have that open hole, and then it goes off, and then for 0, it's just the straight line. So
yeah,
that's how I
but
kind of thought
why
about
is the 0 here?
I don't know.
I mean, this 0 is what? What is that 0 referring to? Which variable?
Y.
It's y, right? So, and when we're doing our intervals, what is the variable that we're looking at? These guys are x's, right? So it's like x is in here, right? So if that 0 came from here, you're not looking at the right thing, right? Because the domain is the x values, and that 0 right there is referring to a y value. So you shouldn't be looking at that.
Gotcha.
But you went off on in the right direction, I think, in terms of graphing it. We do know how to graph that because we did a similar example to this. But what we're going to do is we're going to go through those 3 steps, and we're going to see that even if we didn't graph it, we can still figure out the answer. Yeah, so this is actually not correct. But we'll see why. Guesses on this one. D. No guesses. Did anyone guess this one? Where is that continuous? No sé. Okay. Well, yeah, it's going to be confusing if you're not following the steps. So let's actually see how we would actually go about doing this. Right now, the first two, those are pretty much obvious because they're examples of the elementary continuous functions. But geez, I don't need to like copy that. So let's actually let's jump into this. Let's do this. Let's go. Okay, a f of x equals x squared. Okay, so I want to show that this is actually continuous for real numbers, which I feel like it should be. Like it seems like I can plug in anything and it would work. So what I would do is say, all right, let a be a real number, right? So a is a real number. So now I want to ask myself the question. I said to myself, no, that's not actually right. That question is the limit as x approaches a of f of x equal to f of a, right? That's the question that I'm going to ask. So one, is f of a defined? And I'm going to check that. So I would say yes. F of a equals a squared. We learned how to do that since pre-calc class, right? This is called evaluating the function. Okay, 2, does the limit as x approaches a of f of x exist? And it turns out again, the answer is yes. In fact, if I look at the limit as x approaches a of x squared, I would always get a squared. Now I know on one hand, you can think, well, I can just plug that in and get the answer, but that's kind of circular reasoning for what we're doing here because we can only do that when something is continuous. And here it's like you haven't proven that that's continuous yet. So you would kind of go by first principles, and then you'll show that for any random a that I can pick, whether I'm approaching from the left or approaching from the right, detach. Okay, so we kind of have that. And then I go to my third step. Are the values in 1 and 2 equal? And again, the answer is yes. The limit as x approaches a of x squared is a squared, but that happens to also be f of a. So ding, 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 all three things check out. This means f of x is continuous for at all real numbers a. This means f of x is continuous on negative infinity to infinity. So you can say that is the answer. It's also the same as saying f of x is continuous everywhere. Right, so these are so these all mean the same thing. But of course, if I ask you for one specifically, you need to give me that one specifically. So if the question says, give your answer in interval notation, then the second box is what you should write down for your answer. Otherwise, you're going to lose points because you didn't follow the instructions. Now, this one kind of seems very silly. I get it, but that's because polynomials are so nice. It's kind of like, even if you're doing rigorous calculations, it's kind of like I'm not doing anything because it's like, it's so nice to do within the first place. So yeah, I would actually go through and do these calculations, and that's what worked. Now, the second one we have to work a little bit harder for. So if I go to B in a different color and ask about f of x equals x squared minus 4 over x minus 2. So again, I'm going to go through the three-step process, right? So I would say the following. This is a rational function. No, I don't want to say that. That's begging the question. You would say that after you know this, but we actually want to prove this. I would say we consider, since x equals 2 causes division by 0, we consider for x equals 2 and x not equal to. Okay, so let's talk about x equals 2. If x equals 2, right, you will notice if x equals 2, then f of 2 is equal to 2 squared minus 2 over 2 minus 2, and that is very wrong. That is undefined. So automatically we get that f of x is not continuous at 2. Okay, I just need to show that one of these three things mess up, and I checked the definition, right? So I went to step 1. Is my function defined? No, it's not defined. It's undefined, right? So it's not continuous there. I don't need to check the other two. So now, all right, I know that if I'm at 2, not happening, no bueno, not good. Okay, what if I'm at some other point? So suppose x is not equal to 2. Say x equals a, and where a is not 2. Then I can go and I can check. 1, is f defined? Well, my f of a would be a squared minus 4 over a minus 2, and where that's not 2, this is not 0. So this is just some fraction. And so what I can do is I can treat it like a fraction. I can factor stuff, cancel stuff. Are we good?
I think it's yeah, it was frozen before.
Okay, let me. For some reason, I disconnected from Zoom. Is it my internet that's messing up? Yeah, it looks like it lost the Wi-Fi connection for a second. Okay, we're back, it seems. Okay, so if I plug in a, it's not 2, it's just a fraction that I can reduce. So I get f of a is equal to this. Okay, awesome. 2, does limit as x, why am I writing that out in words? Does limit as x approaches a of f of x exist? Well, if I looked at the limit as x approaches a of x squared minus 4 over x minus 2, we saw that that's going to be a minus x minus 2 times x plus 2 over x minus 2. These guys cancel. I just get the limit as x approaches a of x plus 2. This gives us a plus 2. 3 equal? Yes. So turns out that the limit as x approaches a of f of x is equal to a plus 2, but that's the same value I got when I got f of a if a is not 2. So this means f of x is continuous for all x not equal 2. That is, f of x is continuous on negative infinity to 2 and 2 to infinity. Okay. So I worked through those very carefully just to convince you of them. In practice, you're not going to have to be this pedantic, and I'll show you some of the other examples. So moving forward, we'll allow ourselves to assume continuity of the elementary continuous functions. And you can do this on tests. So that's going to allow us to more directly attack the problem because, it's applied calculus, so it's a little bit too abstract to just say have let a be any number that's not 2. Like it's too abstract. However, if I give us the ability to just assume that these things work whenever we're in the domain, then that actually cuts things down a lot. And we don't have to focus on some random a, we can focus on a specific a, just the one that's not currently in the domain. And that's what we want to do. So that's what we're going to do now. So here is more of what, let's say, a typical example might look like. Yeah, did I grab that one? Okay. Getting closer. Right? The examples on a test might be slightly harder. This is maybe for this problem type, this will be kind of like one of the easy to medium quiz type problem on this topic. A hard quiz type problem would be one that has, variables in here, like one that has like variables in here that you have to figure out what their values are. You might see some of those in the homework, but I probably won't give you many of that. I read the test a long time ago. I don't remember what I put in there. But you might not have to do that. In either case, if you can figure out what we're doing today, you should be fine. And here's more or less what it should look like. Okay, so you're given this random function. It's a piecewise function, which means it's not a list of your elementary continuous functions. It's kind of a mishposh mixture of those guys. So now you're going to say, okay, all right, I need to know what's going to work. So clearly, you would see here the piecewise function is broken up on either side of 2. Okay, so that's what you're going to notice. This is in blue what we notice but don't write. Right. So I'm looking at this problem. Probably the first thing I'm going to take note of is where the pieces are connected. So that's probably the first thing I'm going to think about. Oh, x equals 2 is obviously a point of interest, right? So that's going to matter to me, right? The next thing I'm going to think about is 2. I'm going to think about domains right away, right? Because I know I'm allowed to use the fact that one of these 6 types of functions will be continuous on their domain. So in that regard, I'm going to notice that, hey, this guy, third thing to notice, this is a rational function. So it's continuous on domain. And the domain is all x not equal to 2. All right. Then I'm going to look at this guy. The fourth thing I'm going to notice is that, hey, that's a polynomial. That's continuous everywhere. Right? So these are just some things that are going through my head when I look at this problem, right? So I look at this and I'm like, okay, it says, oh, x is not 2 versus x is 2. Oh, so x equal 2 is something I should be paying attention to because it's different at that point versus away from that point. Okay, so then I'm going to start thinking of, okay, what are the domains of the pieces that I'm looking at? Well, the first one is a rational function. That's continuous on their domain because it's an elementary continuous function. So it's continuous. I'm good as long as x is not 2. I look at the bottom part. Oh, well, that's a polynomial. That's good no matter what. So that guy, the 0 function is going to be fine with no matter where we are. So we're cool. So notice that what I just did was, so step 1, if we want to use steps here like we did for limits, identify potential problematic x values. So these are the x's not in the domain of some function present. And or, in the case of piecewise functions, the x values about which the pieces are stitched together. Right, so that's going to be my step one. And how you go about identifying these potential issues is by doing the kind of thinking that I just wrote down in blue here. So obviously, by going through this thought process, do you notice any potential issues? Where is a potential issue? What x value is going to give me a potential issue?
2.
2. And that's the only one. There's no other x value that came up in this thought process that where I'm like, oh, I need to also look out for x equals 5. Like nothing else came up, right? So like the fifth, so here is what we're going to do. So I would say something like the following. If x not equal to 2, we are continuous. Since we have elementary functions on their domains away from 2. Okay, so now notice what I'm doing here. I'm literally doing the opposite of what we're doing up here, in the sense that up here, I had to just pretend I'm looking at some random real number and I need to know how this is behaving. But here, what I'm actually doing is, because I know that these guys are elementary continuous functions and I know where they work from where they don't, I can essentially eliminate all other real values other than the one that I care about, the potential issue. So we now only examine at x equals 2. So now x equals 2 is the only thing I care about. And so I would go here and I would say, go through the steps, right? So at x equals 2, right? So that's what that's what the beginning looks like. And you don't write this out, but this is kind of what you're thinking, right? So I ask you, where is this function continuous? And it's a piecewise function. You're going to immediately know what are the x values where all the pieces are broken up around. Okay, and within each of these pieces, are there any issues with those functions in terms of their domains, right? So here I notice, all right, this function is broken up around 2. Now each individual function, oh, as long as x is not 2, they're fine. My top function is a rational function. And if I'm not 2, I'm not in the domain. My bottom function is a polynomial. So everything is okay. So now I've identified x equals 2 as the only potential problem. So then I just make a statement here that if x is not 2, we're good, right? However, at x equals 2 needs further examination, right? So that's what you're saying, right? So you're going to just make a statement that you've considered all options for x not equal to. You determined that it was fine because you're looking at elementary functions. And so now you're only going to examine at 2, right? So let's examine 2. It is f of 2 defined. Is f of 2 defined?
No.
What do you mean? Where? Why would you say that? Because it is defined, right? Like if I plug in, it's actually yes, because f of 2, I can actually find that value. What is f of 2?
Oh, right, it's 0.
It's 0.
Yeah.
You need to remember, I mean, the assumption is you guys remember how to read piecewise functions, right? So if I ask you f of 2, you need to look at which one of these intervals has 2 in it, right? So obviously you're not looking at the top because that's when x is not 2. I'm specifically asking about when x is 2. I can read from this piecewise function that when x is 2, the output is 0. So f of 2 equals 0 by definition. So it is defined. So no issues there yet. Let's keep going. 2, does the limit as we approach 2 of f of x exist? Now that's a different question. If I go here, now who do I look at? Well, do I look at this line right here? No, because that line tells me what happens when x equals 2. Does the limit care what happens when x equals 2? The limit does not care what happens at 2, right? This is one of the principles I gave you guys. I don't remember when, but I definitely gave you guys. This is one of the principles I gave you guys. Yeah, here. Limits care about getting close. They do not care whether or not you're at the point. So when I'm considering the limit, I do not care about what's going on at 2. So the part of this piecewise function that tells me, oh, when x equals 2, this is what's going on. I don't care. I'm taking the limit, right? Right? Which means when I'm taking the limit, I care about everyone other than 2. All the people on the left and the right of 2 that is approaching, yeah, I think my Wi-Fi is on phone. That is getting close to 2. I don't care about 2, which means when I'm looking at the limit, I'm looking up here, right? Because the limit doesn't care about the other part, right? So does this exist? Well, the limit as x approaches 2 of f of x, that's the same as the limit as x approaches 2 of this expression, right? Because limit don't care. No, okay, let's not do that. Because the limit does not care about being at x equals 2. It cares about getting close. So we need to examine the interval that contains all the values close to 2. Above, this is the x not equal to part, which has f of x equal to x squared minus 4 over x minus 2 there, right? So of course, you need to know how to read a piecewise function, but you also need to know, depending on what you're looking for, what matters, right? So when x equals 2, it means I need to be able to plug in 2. I need to get at 2. I need to be at 2. So I go to my piecewise function. Which one of these pieces deal with being at 2? Well, the second piece, the bottom piece. It tells me when x equals 2, the output is 0. So if I want to know what's going on at 2, that's the part of the function I look at. It's 0, right? Then I now want to talk about the limit existing. What do I care about at the limit? Do I care about what's going on at 2? Do I care about what's going on at 2? No. What do I care about then? The top part. So when I'm taking the limit, I'm taking the limit of the top part, right? Now we're back into limits, which by now we're experts on this because we've spent a couple classes on limits. I know how to take that limit. try to plug in, right? So here, go through the limit strategies. After thinking about it, you'll see that strategy 2 works here. And again, you're not going to write that down. You're thinking this in your head, right? So you need to identify who should I be taking the limit of, which if you paid attention to all the points and intuitions I gave you before, you would know who you should be paying attention to. So this is the limit we should be paying attention to. So now you're going to be like, how do I take the limit? Well, I try to plug in. Can't plug in, denominator is 0. What's the next thing if I can't plug in? Try to simplify so I can plug in. Can I plug in now? Yeah, the answer is 4. Okay, so now, I mean, it seems like it's taking forever, but that's because I'm really explaining everything. I really want you to understand why I'm doing what I'm doing, what's going on in my head, what should be going on in your head. If you're thinking about something other than what I'm saying, then yeah, don't think about those things anymore. Like it's not useful, whatever it is. This is like the quickest way to think about it. Like you look at the function, you think this, then that, then that. Okay, I know what I'm dealing with now. I care about what's going on at x equals 2, because when x is not 2, we're fine. They're elementary continuous functions. We're good. Examining 2, I need to figure out, is it defined at the point? Does the limit exist at the point? And do these give me the same value? Is it defined at the point? I need to go and figure out when x equals 2 specifically, what does my function do? Here, it gives me 0. Then I have to worry about, does the limit exist at the point? When I look at my function, I need to know what I'm looking at. Should I look at the part that says x is not 2 or the part that says x equals 2? Well, I remember Jhevon told me limits do not care about being at the point. So I do not care about being at 2. I care about everyone else. I care about the guys close to 2. So that's involved in not being 2. So I look at the line that says x is not 2, and that's the function that I examine. Now I take that limit. Then I go back. How do I take that limit? Well, Jhevon told me those limit strategies. I go through those. Boom, now I have the limit, right? So now we're in step 2. So now is the final part. So we are going to ask ourselves, does 1 and 2 agree? Okay, and what do you think? So that's the answer to 1, and that's the answer to 2. Do they agree?
No.
No. So you'd be like, well, f of 2 is equal to 0, but that's actually not equal to the limit as I approach 2, which I just found was 4. They're not the same, right? So what does that mean? And I want you to think very carefully about this. So can someone tell me in like a sentence, what does that mean? What is the conclusion I can make here?
That f of x is not continuous.
No, almost, right? This is why I said carefully. You're missing something.
f of x is not continuous at 2.
Is not continuous at 2. These calculations that I just did was for x at 2, right? So do not make the mistake that you can make some general conclusion here, right? So what I just actually showed with my calculations is at 2 specifically, f is not continuous. Okay, now I can put together the two things that I do know, right? So what did I say before? If x is not 2, we are continuous, right? So that was, maybe I should put that in a different color. So I know figured out earlier that if x is not 2, we are continuous. Then I just discovered now, at 2, we are not continuous. So now I can make a general statement. What would I be able to say in general? What is the final conclusion? Well, it turns out the last statement is the final conclusion, right? F of x is continuous if x is not equal to 2. So as long as we're not 2, we're continuous, but at 2, we're not, right? So that means, to answer the question as stated, f of x is continuous on, well, this interval, going all the way up to 2, and then anything less than 2 and anything greater than 2, we're good. At 2, we're not good, because the limit doesn't equal the value of the function. What happened? Notice what happened is the following. We actually sketched this function before. Here's the graph of f of x. A hole occurred at 4. And that happened when x was 2. Now, someone went in and say, you know what? When x is 2, I'm going to fill in the value 0. So someone came and they filled in this point right here, right? So this is the graph of f. I want you to notice I could not draw that without lifting my pencil off the page. I would have to lift my pencil up to fill in the y value 0 at when x is 2, as opposed to draw the rest of the line. So when this is f of x when x is not 2, and this is f of x when x is 2. That's a disruption. Like I can't get both of those in a fluid continuous motion by sketching this. So we know that the sketch has a hole. Someone came in and they tried to fix the hole, but they did it poorly. Dude, you had one job, right? So yeah, he filled in the wrong thing, right? So now I can say that this guy is not continuous at 2, but it's continuous everywhere else, right? So
If that was a true or false, and someone just asked if all the statement said was f of x is continuous, you would say false because they
you would
didn't
say
specify.
false, right?
They didn't specify.
Because I guess that's a good thing. Also notice that's something I would probably say. Also notice if someone asked, is f of x continuous, right? No specification where, then the answer would be no, it is not a continuous function. How do I know? Because the domain of the function is all real numbers. But it is only continuous on negative infinity to 2, 2 to infinity. So it is not continuous on its domain. Right? The domain, if you look at this function, the domain is everything, right? What x value is not in the domain? They're all in the domain. If my x is not 2, this is the function. So this is the definition of the function for every value, for every input that's not 2. this is the definition of the function for the input that is 2. In other words, I just described to you what the function does for every input, right? Every possible input has an output, right? Which means the domain of this function is all real numbers. However, it's not continuous on all real numbers. We just showed that it's not continuous at 2, which means it's not continuous on its domain, which means it's not a continuous function. It's not continuous in general. I can tell you where it's continuous specifically. It's continuous on this interval. Does that make it a continuous function? No, because its domain is bigger than that interval, right? So it's not continuous on its domain. There are things in the domain of this function that are not in the continuity interval of the function. You'll notice that in this one, and I'll just make that comment and leave you. So this one, it actually turns out that this part D is a continuous function. You'll notice it looks very similar to part C. The only difference is, when x equals 2, I now fill in the value 4, which means someone came down here, saw that 2 had a problem, and they're like, you know what? Let's fill it in with output 4, and they bridge the gap, right? You can now draw the function without lifting your pencil off the page. They didn't fill it out down here. They filled it out where the hole actually was. So now there's no hole anymore, right? So it turns out that example D is actually continuous everywhere. It's continuous on its entire, and it's continuous in general. It's a continuous function. It's continuous on its domain. In fact, this piecewise function in D is equivalent to the line y equals x plus 2. B and C are not equivalent to that function, but D is equivalent to that line. And the line is a polynomial, so it's continuous everywhere. So I'll stop you there. Do these two for next time. We're going to knock these out, and then we're actually going to do something pretty interesting. We're going to solve the rate problem, that age-old question that I said, one of our goals in calculus is to solve this problem. We're going to solve it next time. So that should be interesting. Hopefully you are looking forward to that. But in the meantime, really make sure that you understand continuity. And we'll end there. Thank you for your attention. Hopefully there are no questions. Question?
Yeah, I just had one question.
Yeah.
For the quiz coming up on the syllabus, it says 6 through 8, topics 6 through 8, which includes derivatives. So should we just negate that and then just focus on limits?
It depends on what section, because we are going to do derivatives on Friday.
Okay. Oh, okay, gotcha. So all right, just whatever we got up to.
Probably okay. Yeah.
Okay, gotcha. Just making sure. Thank you.
Okay. Yeah. So with that said, we'll sign off. I will see you guys in the next one. Ciao.